Calculus Unit 5, Day 41 notes. The objective, apply major theorems numerically, graphically, and verbally. What are those major theorems? Intermediate value theorem, extreme value theorem, Rolle's theorem, and mean value theorem. We're going to take a look at these uh, definitions, but then I also want to take a quick little review graphically of what they mean. And then obviously some of the problems are going to, same thing, look at them numerically, graphically, and verbally. So applying theorems in calculus. So intermediate value theorem, extreme value theorem, Rolle's theorem, and mean value theorem. So let's remember what each of these theorems says about a function, then we'll quickly sketch a graph of what that means. So the intermediate value theorem, the IVT, which we did a few days ago in notes, um, states that if f of x is continuous, and all of these have to be continuous. Continuous means no breaks. You can't have a hole, you can't have a jump discontinuity, you can't have a vertical asymptote, so they all have to be continuous. On the closed interval from a to b, and the y value is but falls somewhere between the y values of those endpoints, and again, it doesn't matter whether f of a is smaller or f of b is smaller, then there's at least one value, that's supposed to be an e right there, one value of c on that open interval a to b such that f of c equals y. All right, so what the heck does that mean? Again, it has to be continuous. So, I, and again, I was going to draw an xy axis. It doesn't even matter what that uh, where the xy axis is. So if I have some continuous function, again, it doesn't matter what that means. And let's go up a little bit more. Okay, so um, this point right here is, that's going to be f of a. There's a, so the x value is a. Here, the x value is b. And again, its y value is f of b. So what they're saying is if I take some value c, and it doesn't matter where, and there could be multiple values, but if I choose any y value that I'm going to call f of c, as long as it's in between f of a and f of b, then there must exist some value c. And what they're saying is that that c value must fall between the a and b. Here's b, here's a, and that's all they're saying. Um, and again, you could have an f of c. You could have multiple places where it happens. Here would be an f of c where that would fall at a few different places. So what they're saying is, hey, that f of c is going to be equal to um, that y value. Okay, so that's all they're saying. Hey, if you're given some interval, as long as it's continuous, if there's a y value that's between the y values of the endpoints, and again, this is intermediate, which is in the middle, if there's a y value in between those y values of the endpoints, then the x value also has to be in the middle of those endpoints. Okay? Next one is extreme value theorem, the EVT. So again, starting with it has to be continuous. Again, think of what extreme value means. It means absolute max, absolute min. So if the function is continuous on a closed interval from a to b, then there must be an absolute max or an absolute min. And again, it has to be continuous, but it's a closed interval, meaning it doesn't go on and on forever. That there has to be an absolute max and an absolute min on the closed interval from a to b. Where could these absolute extreme occur on the interval? It could be either at endpoint A, endpoint B, or any value in between. So let's look at a couple examples of this. Okay, so first example might be, um, here's my interval, closed interval, which means again it doesn't go on and on forever in that direction, doesn't go on and on forever in that direction. So it's closed. What the extreme value theorem says is that there must be an absolute min and an absolute max. Well, I'm going to see, hey, this is going to be my absolute max, absolute min, excuse me, and this is going to be my absolute max. It can be the absolute max at the end point if it's closed, meaning it includes that point. If it didn't, then we wouldn't have an absolute max. Okay, so absolute min, absolute max. Uh, I could have, and again, it doesn't say anything about having to be differentiable. So you could have corners, you could have cusps. Um, this would be your absolute max. This would be your absolute min. Question always comes up, well, what if we just have this segment? And what I'm going to find out is it's on the closed interval. So there's your absolute min, there's your absolute max. And again, that's sometimes it can occur at the endpoint, sometimes it doesn't occur at the endpoints. Okay, so that is the extreme value theorem. All right, next is Rolle's theorem. So if the function is continuous on the closed interval from A to B, and now we're talking about it has to be differentiable. So that excludes any corners, any cusps um, on the open interval from A to B. And for the Rolle's theorem, the value of the function at the endpoints must be equal. F of A must be equal to F of B. Then we're going to guarantee that there's a value of C on the open interval A to B such that the derivative at that value is equal to 0. So that's kind of telling us it's going to be a relative min or a relative max. So again, can't be anything with any corners. So continuous and differentiable. It doesn't matter how many places it goes. And one of the keys is that if this is A and this is your B value for X, F of A must equal F of B. So that value of the Y, mine's kind of close, there you go. So what this says is we're going to guarantee that there's at least one value C where F prime of C, which is the derivative of the tangent line, equals 0. Okay, obviously in this example, I have a couple of them. Okay, but as long as it's continuous, hey, I would see that this would be derivative of 0. Okay, so I might say, well, what if I have a horizontal segment? Well, again, this derivative is 0. The derivative of that is 0. So there's a bunch of infinite number of ones. And again, it wouldn't be, you can't include the endpoints, okay, because you can't take the derivative at the endpoint. Okay, and lastly, the mean value theorem, MVT. Again, mean, average. So once again, if f of x is continuous on the closed interval from A to B and differentiable, which means you have to take the derivative, which eliminates corners, eliminates cusps, on the open interval from A to B, then there's guaranteed to exist a value of C on this open interval AB such that the derivative of the tangent line is going to be equal to, which again, the derivative, which is the slope of the tangent line, is going to be equal to the slope of the secant line. Let me just quickly write that down. What is f prime of C equal to? That is, this is the slope of the tangent line, and somewhere on that interval, the slope of the tangent line must equal the slope of the secant line. Okay, and as we stated before, back in day 40 notes, this is the average rate of change, secant line. Again, we think of mean, think of average, and this is the instantaneous rate of change. And that's the slope of the tangent line. Okay, and let's look at this example. And hopefully this clears up the difference and similarities between these, because this is similar to Rolle's theorem, except it still has to be continuous, still has to be differentiable, except now I don't need one endpoint to equal the other endpoint. Okay, so if I have this, I know my, that's an awful secant line. Let's do that again. Cheat, do this. So if that's my secant line, that's the average rate of change. That's going to have a certain derivative. Let's go back to this. I think right about here, hey, those slopes are the same. And maybe right here, those slopes are all the same. So the mean value theorem guarantees at least one value of C. And again, what were we talking about? We are saying my beginning point, so this is A, has a value of f of A. And the only difference between the mean value theorem and Rolle's theorem is Rolle's theorem says that f of A and f of B have to be the same. These do not. Um, and there's my B, that we're now saying, hey, there's some value C such that the slope of this tangent line is going to be equal to the slope of this secant line. And again, change in y, that's where the FA minus FB, that's the rise, all over the run, A minus B. And again, this could also be C, and the slope of that tangent line is going to be equal to the slope of the secant line. Okay, sounds like a lot. Hopefully, when we work on this for the second day, on day 41, it'll get a little bit easier. Okay, day 41 notes, part one. Let's look at some of these examples.